Alright, so let's talk about this topic using the general properties of reaction enthalpy. Now when you look at this problem and look at what you see this value right here. Now this is what we call the reaction enthalpy. And sometimes you see it written like this, where you have this was the enthalpy change for this particular reaction. However, often this is what is done in ALEKS. You see the subscript here. The subscript RxN, which stands for reaction, is omitted. And you only see this delta H for the enthalpy changes of the reactions. Now, as you see in this example here, the enthalpy change of a reaction can be positive, or as in this case, it can be negative. What does a negative change in enthalpy tell you? Well, it tells me that for this process, the reaction is exothermic, or heat is released by the system. So again, if delta H is negative, then that means the process is exothermic. If delta H is positive, then it is an endothermic process. Heat is being taken in from the surroundings into the system, of the reaction system itself. So how can we tackle this problem? What other background information do we need to know? Well, we need to understand what this, often referred to as a thermochemical equation, is telling us and how we can interpret the information presented here. So when I look at this reaction here, this thermochemical equation, I see that it is the decomposition of this substance, which is glucose. It's breaking down into this substance, methane, and this substance, carbon dioxide. And as I read this thermochemical equation, I see it tells me that for every 1 mole of this, it breaks down into 3 moles of methane and 3 moles of carbon dioxide. And I also see that this reaction is an exothermic process. This enthalpy change tells me how much heat is given off when 1 mole of this breaks down into 3 moles of this and 3 moles of this. So from this information given, this enthalpy change tells me the heat change per mole of the reaction as it is written with these stoichiometric coefficients. So as you've already guessed, for these problems, it's extremely important to make sure that the chemical equation is balanced. So let's take a quick look at these guidelines that we can use to interpret thermochemical equations. Look at guideline number 1. The stoichiometric coefficients always refer to the number of moles of a substance. So this is telling me in this example that when I have 1 mole of ice and it melts to 1 mole of liquid water, that this is the amount of heat. 6.01 kilojoules of heat must be put into that system for it to do that. The second guideline, and this is from the PowerPoint in the slides, it tells you that if you reverse a reaction, the sign of delta H, or the enthalpy change, has the same magnitude, same number, but opposite direction, opposite sign. So in this example, we still have the same substance, water, but it's in different phases. Here we were melting ice to liquid water. Here we are freezing liquid water to ice. We still have 1 mole of liquid water, and we are freezing it to produce 1 mole of ice. And so the enthalpy change for this reaction has the same magnitude, the same value, but look at the sign. Here it's negative, whereas here it was positive. Well, what do we know when delta H is positive? What does that mean? It's an endothermic process, meaning heat is taking in from the surroundings into the system. Well, what about when delta H is negative? Well, that is an exothermic process, meaning heat is given off to the surroundings from the system. Well, let's look at the third guideline here. It says that if you multiply both sides of the equation by a factor n, then delta H must also change by the same factor. So if I take this same reaction we've been looking at, and so here I am melting water again. I'm going from ice to liquid water, but I doubled the amount of matter now. How do I know I doubled the amount of matter? Well, look at this stoichiometric coefficient. Here it's 2, whereas here it was 1. I have twice the amount of ice here, and I'm melting it to produce twice the amount of water. How do I determine the enthalpy change for this particular reaction? Well, I'm going to double the enthalpy change, that value. So that means that delta H for this particular process would be the same that it was here, but doubled. And one last guideline for interpreting and working with thermochemical equations is the realization that the physical states of all reactants and products must be specified in the thermochemical equations. They do matter. In this case, even though we have the same chemical substance over and over and over again, it's in a different state of matter. We have here ice, solid water, liquid water, and here we have water vapor. Well, the energy states of water in every one of these different phases is different, which is why the enthalpy change for these processes are also different. So what you'd have to do is, when you're working with a thermochemical equation, you need to understand what the physical state of the reactants and products are so that you make sure that you're working with the correct enthalpy values. And these will either be given to you in the problem or in a given table of substances. So now back to the example problem here in this particular topic. So let's tackle these 3 pieces of this question. So here we have the reaction. We have methane and carbon dioxide being converted to glucose. If you look, we have the exact same substances, except the reactants and products have been switched. So this is the reverse of this reaction. You see glucose is the reactant here, but down here, glucose is the product. Well, which one of those 4 guidelines that we just looked at correspond to this particular part of this example problem? That would be number 2. If you reverse a reaction, the sign of delta H changes. So if we look here, we have reversed the reaction, and that is it. We haven't changed anything else. How do I know? Well, I had 1 mole of glucose here. I still have 1 mole here. I have 3 moles of this and 3 moles of this. The only thing that changed was that I reversed the process. And so this answer would be the same exact enthalpy change for this process, but the sign would be different. And so delta H would be equal to positive 132 kilojoules. Now we look at the second example here. I've got half a mole of methane reacting with half a mole of carbon dioxide, and it's producing 1/6 of a mole of glucose. Well, again, we have reversed the process. So this process is reversed from the original process, and I have reduced the number of moles of substances involved in this reaction. So if I go back here, let's see what we're dealing with. We have reversed the reaction, and we have also changed the amounts of the substances involved. Well, how did we change it? It looks like we divided everything by 6. How do I know? Well, if I have 1 mole here originally, here I have 1/6 of a mole. So I divided it by 6. What's 3 divided by 6? It's 1/2. 3 divided by 6. It's 1/2, 1/2. Okay? So, again, here we have reversed the process, and we have also reduced the amounts of each substances involved, each of the reactants and products, by a factor of divided by 6. Okay? So what would the enthalpy change for this process be? Well, we know it's going to be this, and because I reversed it, it's going to not be negative 132 kilojoules, but positive 132 kilojoules. And also, I reduced the amount of matter in this process by a factor of 6, so it'll be positive 132 kilojoules divided by 6, which will give me positive 22. And I'm going to keep 3 significant figures, so 22.0 kilojoules. And let's look at the last part of this problem here. Now I have this process. It's the decomposition of glucose to methane and carbon dioxide. It looks like it's the exact same process here in the sense that it is not reversed. Okay, so that means that the enthalpy change for this process is going to be negative just like it is here, which means it's going to be exothermic. So it's going to give off heat. Well, I also have to check and see if I've changed the amounts of the substances involved in this process here in this third example, and it looks like I have. The enthalpy change for this reaction as written with 1 mole of C6H12O6 and 3 moles of CH4 and 3 moles of CH2 is negative 132. Well, here I don't have 1 mole of C6H12O6, but I have a third of a mole. I have 1 mole of methane and 1 mole of CO2. What that tells me is I reduced the amounts of the substances in this process by dividing the original amounts by 3. What's 1 divided by 3? 1/3. What's 3 divided by 3? 1. What's 3 divided by 3 here? 1. So in this case, all I've done is divide the substance amounts by 3. And so to find the enthalpy change for this reaction, I'm going to take the enthalpy change for the given reaction, which was negative 132 kilojoules, and I'm going to divide that by 3. The final answer should be negative because, again, I have not reversed the process. It should still be exothermic. And for my answer, sticking with 3 significant figures, I get negative 44.0 kilojoules.